Just looking out for the flyer for the meeting. Right. So this meeting is going to be, this evening we have Eqbal Hussain from the British Geological Society coming to talk to us about a recipe for disaster. For those of you that don't know Eqbal, he is the topic lead for multi-hazard systems and a remote sensing geoscientist at the British Geological Survey. His research focuses on the use of satellite imagery to understand Earth processes, particularly those related to natural hazards such as earthquakes, landslides, and sand dune migration. Eqbal is an advocate for holistic multi-hazard approaches to understanding and managing the impact of natural hazards to society. Please welcome Eqbal, and over to you, Eqbal.
Thank you, Bridget. So I'll just share my slides. Is that okay for you, Bridget?
Yeah, we can see it.
Great, thank you. So I'll get started. Just moving you up a bit. Okay, great. So thank you, everyone. Thanks for the invitation. It's a pleasure to be here, speaking to you all. Shame I can't be there in person, but it's great that you guys have managed to keep these talks going over the last couple of years, at least on the virtual sphere. So good on you all. Today I'm going to talk about something that's a little bit more broader perspective on my work on natural hazards, and the age-old question of when and why do hazards turn into disasters? And that's really the crux of the talk. What turns a natural hazard into a so-called natural disaster? I put that in inverted commas because there's no such thing as a natural disaster, and that's really something that we're trying to move away from using that terminology. But why I'm going to talk about why that's the case, I'm going to try and talk about in this talk. But something I want you all to be aware of is that everything I'm going to say today is relevant to earthquakes. I'll explain each of the ideas using earthquakes as a hazard, which is the one I know most. But these ideas are all relevant to all hazards, whether they're windstorms, hurricanes, heat waves, floods, doesn't matter. The ideas are general, but I'm going to illustrate them with earthquakes. So to begin with, quite simply, what is an earthquake? Just in case you have any younger members of the audience, this is an example of what happens in an earthquake. This is something taken from California, where this large crack going across the image here has offset these field furrows by about 50 centimeters to the right. And here's another example in the Nevada deserts, where this old dry river valley has been offset by about 4 meters in this case in an earthquake. So that's what happens in an earthquake. What is an earthquake? Quite simply, an earthquake is the release of strain energy in the ground, usually along fractures that are called faults. And the traditional view of these things is that there's a large cracks in the ground where they're stuck by some strength, frictional strength, and the plates are constantly moving around, and this friction is overcome suddenly, and that release of energy when that frictional strength is overcome is what is an earthquake. Here's a simple model of one looking down onto the ground. The fault itself is going across the screen, and the top half of the image is moving to the right, the bottom half is moving to the left. But the fault itself is stuck. Oh, this is meant to be a video. Seem to work. There we go. And so the plates are moving, but the fault's stuck, which means that the strain energy is being built up on this fault until it reaches a certain point that overcomes a critical friction level, and that thing ruptures, and that's what we call an earthquake. So where do these things happen? This is a map of all the large earthquakes of the last 30 years. And quite the very obvious observations that you can see there's these long linear lines of earthquakes in the oceans, and we've known that for about 50, 60, 70 years now, and that's where the plates were drawn, plate boundaries were drawn. And this is not a new observation. There are long linear lines of earthquakes in the oceans, and that's where the plate boundaries are marked. But if we look into the continental interiors here, you'll notice that you can see the Indian Ocean plate boundary here, this linear band, which is about 100 kilometers wide. And that's quite a simple observation. But if you look in the continents, this zone of earthquakes, and so from India to northern Mongolia, it's about 3,000 kilometers. So we can't really put a line through there and say that's the plate boundary between Africa and Asia, Eurasia. So what we say here is that on the continents, earthquakes are distributed. So the old traditional method, or the old traditional view of plate tectonics doesn't really work in the continental interiors. So there's more at play here, and the tectonics and the geology is a little bit more complicated. But what matters for us is, that's where a lot of the earthquakes happen. That's where a lot of people live. So we can start with the simple sort of hypothesis that larger earthquakes kill more people. Larger earthquakes tend to be more energetic, and they just certainly produce more seismic waves and more. And so we can make that, and we can plot all the large earthquakes and the fatalities against each other on this graph here in log scale. And the first observation is that there is generally a positive trend where large earthquakes tend to kill more people. But my view on this is that it's not so simple, and I'll illustrate that with a couple of examples. So that in the middle there is Nepal in 2015, a magnitude 7.8 earthquake that killed around 9,000 people, and that's a lot of people, and it's a relatively large earthquake, and it falls right in the middle of this sort of positive trend zone we've drawn on here. But the largest earthquake we've ever measured was a magnitude 9.5 in Chile in 1960s. And so this is a gigantic earthquake, and that killed around 3,000 people, which is still a lot of people, but the earthquake was, 60, 70 times larger than the magnitude 8. So it's this, the losses were disproportionately low given the size of the earthquake, especially when you consider Sumatra up there. Here's another example, Haiti in 2010. A magnitude 7.1 earthquake killed anywhere between 80 to 300,000 people. The number there is debated because of various political reasons, which we won't go into now. So that's magnitude 7.1. That's now above the sort of trend line. It's a smaller magnitude earthquake, but tend to kill more than the larger earthquakes. Here's another example in Pakistan, 2011, a magnitude 7.1 again, same as Haiti, but it killed 3 people actually. And so, in fact, it actually killed 5 people in general, but the net death rate is 3 because the shaking induced 2 women to go into labor early. So you actually had 2 births and 5 deaths, which, and it all goes to show that, it's not so simple. Large earthquakes killing more people isn't the whole story. And what I'm trying to show you here is that there are more aspects at play here. And actually, this is the answer to that question: what makes a hazard into a disaster? It's these 4 things: exposure, poverty, corruption, and ignorance. And just because I couldn't resist the temptation, I call these the 4 horsemen of disaster risk. And for the rest of this talk, or at least for the first half of this talk, I'm going to go through each one of these and show you why these are relevant to earthquakes and all hazards in general. So first, exposure, first horseman. What do we mean by exposure? That's simply, where do people live and what kind of buildings do they live in? And the first half of that question is quite easy to answer. We know where people live, and we can use satellites and other various census things to measure it and plot maps of where the population density is largest and where it's lowest. And this is a map from 2015, so this is already a few years old now, from using satellite data to plot densities of people. And again, the simplest observations are often the most important. The world's population density isn't evenly distributed across the planet. There's a large zones of the world that are practically empty, and there are other large parts of the world that are really full. So especially this band going from Europe through the Middle East, through Central Asia, through South Asia to East Asia, this zone has very high population density. And that's going to matter, because that's going to matter in terms of our sort of susceptibility to hazards. The other half of this question, what kind of buildings they live in, that's a harder problem to address, because we can't go and record every building in the world. that's simply impossible for any one person or one organization to do. So we had to make estimates of the kind of buildings that people live in, because that's really what matters when it comes to earthquake hazard. And so, and we have actually fixed this problem yet. So if anyone has a really cool idea on how to do that, please get in touch, because it's one of those problems that we really don't know what to do with, how to get on top of it. And so, and the challenge being, a lot of buildings were built in the past and they're being built on top of. So we really don't know what's hidden inside the walls of many of these buildings. And buildings always change. Cities are constantly expanding and changing. And so keeping up to date is one of the real challenges of monitoring and modeling disasters. But, you know, we can use some tricks. So believe it or not, unsurprisingly, and the United States has been spying on the world for a long time. And even since the 60s, they've had satellites in space spying on everywhere in the world, mostly China and Russia. And to a degree that using the quality of satellites that are commercially available now. And they were doing that 60 years ago. Amazingly, about 10 years ago, 15 years ago, a lot of this old satellite imagery were declassified and they're made available to the public. So this is one of them here. These are called Corona images. It's taken from 1970 of Santiago, the capital of Chile. And this red line here is an active fault that we mapped a few years ago. And this is all the white dots here are the buildings. This is a radar image. And so the white buildings reflect white very well. And these sort of, that's an alluvial fan there for those of you who are keyed into this. So that's 1970. And this is the same image, same place in 2014. So if I go back and forth, I want to just point out a couple of things. See this hill here? I want you to see this hill and this alluvial fan. In the 1970s, these were all fields and that was just an empty hill. And now they're full of buildings. And this is the fault. And that hasn't had an earthquake in hundreds of years. And now the whole city has been built on top of the fault. So the fault itself is underneath buildings. These are luxury homes with swimming pools. A lot of the black dots are swimming pools. And the fault is dipping to the left, to the right. So it's on the hanging wall of the fault, which is, those of you who do seismology know that's the most dangerous part of the fault because you're right on top of it. So, you know, those people's exposure has increased in that time. Just looking at the side here. Yeah, so the exposure of those people to that earthquake has increased quite dramatically, and the same for the whole city. So that's a change in exposure that has happened in the time, in what we call the interseismic period of that fault. This is a more broader global look. Roger Billam did this compilation quite a few years ago now. Every square here represents an earthquake that has killed a lot of people. And the bigger the square, the more people it's killed. And this yellow is a general representation of where the big subduction zones are in the world. This is where you have the largest earthquakes, the real big 9s and big 8s. That they all tend to happen on the subduction zones. But interestingly, most deaths happen in that red circle, far away from the subduction zones. In fact, 85% of all the world's fatal earthquakes have happened in that red circle, oval. So away from the places that tend to have the biggest earthquakes. So this is already showing us this discrepancy between the size of earthquakes and actually where the deaths happen. And what we say here is some countries or some regions have a much higher exposure to earthquakes, and location clearly matters. Here's another way of showing this. So these are all this compilation is 20 years old now. So 15 years old, well, 12 years old now. And so it needs to be updated. But at the time, from 1900 to 2011, these were all the large subduction zone earthquakes that have happened around the world, and magnitudes on the bottom and the fatalities on the left. So 2 large magnitude 9s had killed, around 250,000 people, which is an awful number in itself. But if I put on top here the continental earthquakes, the ones away from the subduction zones, the 2 patterns emerge. First, they tend to be smaller in magnitudes. The average magnitude is around 7 or 7.5 here in terms of fatal earthquakes, and they tend to kill a lot more people. So, and that's really important. Most fatalities in earthquakes happen in the continental interiors in earthquakes between magnitudes 6.5 to 8 or 7 to 8. So that's a real important observation here. So that's the first horseman, exposure. Second horseman, poverty. And this really is a good news story to begin with. And it's probably my favorite good news story that I wish everyone knew, regardless of your background. And I'm going to try and explain it here. So this is a map of the world's global population since around 1820 to where it was around 1 billion to around, 8 billion now, exactly almost as of last month. So there are 8 billion people in the world, and we know this exponential growth curve. And this year, it's a fraction of the number of people who have lived in extreme poverty. So extreme poverty is a really well defined. As of now, it's earning less than $2.1 a day, international dollars a day. So anyone who earns less than that is in that red zone. And that's, this is really, really poor people and people who can't afford to feed themselves and their families on a daily basis. So that's an awful thing to be. And, around 1820, something like 78% of the world lived in extreme poverty. I mean, 78% of the world could not feed themselves on a daily basis. And the amazing transition that's happened over the last 200 years is this number, this fraction. Despite the fact the world's population is grown exponentially, the fraction of people living in extreme poverty has been dropping steadily and at a faster rate since the last 50 years. Now down to around 8% of people in the world live in extreme poverty, which is an amazing good news story. And the COVID pandemic had a slight change on this, but overall, that trajectory has been good. So good that the media could have run this headline. 137,000 people escaped from extreme poverty since yesterday. Every media outlet in the world could have run that headline every single day for the past 25 years. That's how many people come out of extreme poverty all the time. And that's an amazing thing. But so why is this a horseman in my disaster risk? It's because extremely poor people live in houses like this, usually built of local materials, wood, bamboo, mud, and straw roofs. And amazingly, these are pretty resilient to earthquake shaking. It's the old nursery rhyme or that children's story of the willow and swaying in the wind. Wood and local materials like this can absorb a lot of energy. And even if the building did collapse, the straw roof is unlikely to kill you. But when people come out of extreme poverty, they want to do this. One of the first things they do is, amazingly, this trend is pretty much the same everywhere in the world. When people come out of extreme poverty, one of the first things they do is get a mobile phone, get some sort of electricity, take their kids to school. Actually, that's probably the first thing they do, send their kids to school. And then they want to build a home for themselves. And this is a photo I took in Bangladesh a few years ago. This family currently lives in this sort of a bamboo mud house with a tin roof in the background. But they've come out of extreme poverty, and what they want to do is build a home for themselves, and it's quite normal. But they're not trained architects. They're not engineers. They don't really know how to build a house properly. But they've got a little bit of money now that they can spend on themselves, so they will do it themselves. But remember, these are still very poor people. They're just coming out of extreme poverty. They're still poor. So they still want to minimize costs. What they've done here, if you look at the bricks are side on, not flat. Most houses outside, and if you go outside and look on the way home, you'll see the bricks are flat. And that increases the surface area of the ground. But you need more bricks to build the wall. So the wall in the inset is stronger, but it needs more bricks. The wall here is side on, needs fewer bricks, but the surface area connection to the ground is a lot less. So this is a weak wall. Here's another example. This family here on the left lived in this tin house here, a bamboo tin house, and then they built this brick masonry building on the right. Exactly same principles, brick side on, number of rods in the columns, absolutely not enough. This house will probably fall in an earthquake. The one next to it probably won't. But this is a sign of their growth out of extreme poverty. So unfortunately, the jump from extreme poverty to poor, so this is really important, extremely poor to poor, these are still poor people, increases their risk to earthquake shaking. So this is where it's unfortunately quite sad. And the age-old sort of saying from Nicholas and Bryce is that is the reason. Earthquakes don't kill people, buildings do. And this growth, this unfortunate zone where you're still poor is, I think, probably the highest risk group in the world to earthquake shaking. The third horseman, and this is one of my favorite, corruption. Simply defined, it's the misuse of interested power for private gain. So I've trusted you to do something, and you've misused that trust for your own personal gain. And you don't need me to tell you that corruption is deadly. This is a picture from Kenya. So what does that mean in terms of our earthquake hazards? So we know that it's buildings that kill people in earthquakes, and it's all about how the building's built. So a very simplified view of the optimal ratio in engineering is 1 bag cement and 3 bags sand, mix them together with some water, and that gives you a really strong cement mortar. And if your house is built with that, then it's great. It's the optimal sort of strength. But cement is expensive compared to sand. So if you're a corrupt contractor, what you might do is you mix 1 bag cement and 6 bags sand. And once you mix it with water and everything, it looks the same, but it doesn't behave the same. It's not as strong anymore. You may have pocketed that 1 bag cement worth of money, but the house you build is no longer up to standard. So that's one form of corruption. Another form of corruption is not building the house properly to begin with. So again, same idea here. This is India, bricks side on. And most importantly, I want to show you here is this column. The columns are where most of the strength lies in a building. And the strength of the column lies in the number of rebar rods in it. And in this column, you see there's only 1 rod. Really, it should be at least 4 rods in a column for it to have a good amount of strength. But the problem is, once you cut that rebar rod at the top, no one knows. No one can look into that pillar anymore to see how many rebar rods you've used. So the contractor may choose to pocket the money for those rods, and no one will know. So that's another form of corruption. And the third one is putting the buildings in the wrong place. So it doesn't take a genius geologist to tell you that this is a very dangerous place to be living in. These cliff slopes, this is from Turkey, are very extremely unstable. Some of it's crumbling away, you can see already here. It won't take an earthquake. It will take just heavy rainfall, and these cliffs will come down in a landslide. So these buildings should not be there. And that's just bad planning regulation or bad applications of, or even no application of planning here. Homes being built in places they shouldn't be. And the last one, almost every country in the world, believe it or not, Haiti, I think, has the earliest building regulation in the world. And it still had that awful earthquake 10 odd years ago. So almost every country in the world has regulations in place about how to build buildings properly and safely. The challenge has always been is implementing those regulations and enforcing them, particularly in poor countries where there aren't enough government contractors, government inspectors even, and they're often underpaid. So they'll take the money and just sign your building off. And that's unfortunately what happens a lot. So corruption is one of those strange things that you can't really measure. You can't actually say, okay, how corrupt is a country, because it's a very difficult measure it's a very social measure. It's hard to put numbers on it. But these guys have been trying to do that for a long time now. Transparency International for at least 25, 30 years now. They've been measuring not the absolute value of corruption in a country, but the perceived level of corruption in a country. So this is quite important. It's the perception of corruption. And so every country in the world, they give a score between 0 and 100, and 0 being it's devil, completely, absolutely corrupt. There's no hope whatsoever. And 100 being no corruption at all, angelic. No, there's nothing wrong there. And sadly, no country scores 100, but also no country scores 0, thankfully. Just in case you're interested, and probably not surprised, that the best countries in the world are New Zealand and the Scandinavian countries. They're scored in the high 80s, low 90s. UK scores around 76, I think, similar to the US. But what matters here is these are the 5 most fatal earthquakes in the last 20 years. And they all happen in orange or red countries. And that's really worrying. So if you look at a scale of not 100, not being the devil, 100 being angel, the 50 mark is the middle, where you're not you're, one way or the other. You're just right in the middle. So 2/3 of all countries in the world have a score less than 50, meaning they are more corrupt than not. And that's really worrying. And why does that matter? What can we do with that, knowing that? So again, this is the same score, corruption score. Instead of 0 to 100, it's 0 to 10, but the same idea. If you plot every country against their gross national income, so the wealth of a country, you see the strange, interesting positive trend. And what this positive trend tells you is that if you fall on the line, you're just as corrupt as we expect you to be. So countries like the USA, UK fall on this line. Japan, they fall on the line. Given how wealthy they are, their expected level of corruption is about that, and they are about that. But if you fall above the line, for countries like Chile, for example, we expected their corruption levels to be down there. They're more corrupt, but they're not. They're less corrupt than we expected them to be, which is amazing. If you fall below the line, you're more corrupt than we expected you to be. Countries like Italy, for example, we expected it to be there based on the wealth of the country, but it falls down there. Turkey, Russia, Mexico, these all fall below the line. And why does this matter? It matters because the construction industry is the most corrupt segment of the global economy. It is one of the largest segments of the global economy. I think it's like good, don't remember now, 5, 10, 20% of the global economy. And it's also the most corrupt. So, a lot of these countries are building homes badly, basically, down there. So if I color this in, those are the good guys. They're less corrupt than we expect them to be. Those are the bad guys. They're more corrupt. And this is where everything goes wrong. The countries are very poor, a lot of bad practice in terms of building codes and building implementation, and the corruption is rife. So the orange and red is where the most deaths happen in earthquakes. So much so that 83% of all earthquakes in the last 30 odd years were in low-income corrupt nations. Corruption kills. And so, a slight digression, why do buildings fall? Buildings fall because of one very simple reason: the fatal attraction of gravity. Everything wants to go horizontal. And as soon as it's passed vertically, it wants to go flat. And that's the only reason why buildings fall. Small, which means, if you're close to the ground, you're less likely to fall. So single-story buildings tend to be safer. Buildings built with wood and thatch and there's energy-absorbing materials tend to be safer. Multi-story buildings, if they can be very safe if they're built properly, but if they're not built well, it's just a big twig waiting to fall over. On top of the structures, you see this a lot in places like Taiwan and in China. We used to anyway, where they build these big blocks of block building, and make the ground floor a beautiful shopping mall, and the top floor is residential. But because it's a shopping center, they want to have big open spaces, lots of display sections. So they don't have many walls and they don't have many pillars. So this whole ground floor is a weak floor. And what tends to happen in earthquakes is that the whole top part, the residential part, just pancakes down to the shopping center. And so everyone who lives in the top buildings are fine. Everyone who went shopping that day gets crushed. And that's surprising and worryingly more common than you'd think it should be. Here's what happens in an earthquake. This is from Turkey. I think this is Turkey, 1999, I think. The house in the background, this concrete building, again, everyone's probably fine in there. It's just that weak ground section collapsed on one side and toppled over. This building here is in the foreground. It's built a wooden frame. You can see all the triangles in there, in that frame. If you remember your DT classes from school, the triangle is the most simple rigid structure you can make. And this house has got plenty of them, even though it's made of wood. And so it survived. And that's really quite straightforward, actually. The more triangles you have in your frame, the stronger your building is going to be. And this is a photo I took in Bhutan a few years ago. So in almost every measure, this new home that's been built here, this new block, it's built well. The pillars are absolutely enormous. They have huge pillars here with lots and lots of rebar rods. So, everything's fine. They follow the building codes. This building has been built well. But I want to draw your eye to is here, this section here. I'll show you this close up. So on this side of the building, all the bricks are in between the pillars, right? And on this side of the building, for some odd reason, they've decided to put all the bricks on the outside of the pillars. So when an earthquake happens, those things have got nothing really to hold them up. They're going to come raining down. And one of the main reasons we say, if there is an earthquake, not to run outside while the building is still shaking is because all these bricks raining down on you is probably what's going to kill you more likely to kill you. So this is just bad design, or just the fourth horseman, ignorance. Maybe they just didn't know that this is what they should have done or what they needed to do. And it's often hard to tell. It's often hard to tell the difference between ignorance and corruption, because this gentleman here is putting one rebar rod into their pillar. Is that because they didn't know that it needed at least 4? Because these people aren't trained masons, trained home builders? Something like 90% of all homes in poor countries are built by a homeowner with no formal training in how to do it. So, it's hard to tell what's corruption and what's ignorance here. And ignorance not in a sort of derogatory way, it's more no training sense. And that's often the big danger here. And, often the engineering principles are really quite straightforward. So this is a photo from, I think this is from California, where this pillar has been just pulled out to the foundation by the earthquake. And the fix to that is really quite straightforward. Nature has done it for millions of years. If you look at a tree, it buttresses near the base, and that gives it a lot of stability. You can do the same with buildings, or pillars anyway. These rebar rods can go in, down to the ground, and they can be buttressed out or bent out a little bit. That doesn't cost any more money, but that then gives it that pillar, that vertical strength that it needs to stop it being pulled out of the ground in an earthquake. Here's an example. This is a lesson California learned a few years ago in the 1970s. In this particular earthquake, this is a bridge. The bridge on the top pushed down, the ground pushed up, and the pillar exploded outwards. And because that just couldn't handle it. And the simple fix to that was really quite straightforward. They had enough rods in the pillar to give it that vertical strength, but they didn't have anything to give it the horizontal strength. And all that needed is stirrups. And now there are regulations in place that every certain, I think 15 centimeters, there's another simple bracket and all the way up the pillar that gives it that horizontal, that sort of the y direction strength. And that doesn't cost a lot of money. Those stirrups are quite inexpensive. It doesn't cost a lot more money to give it that strength. This is my favorite example. Those of you who have been lucky enough to travel to poorer countries in the world will see a lot of this, where the pillar going up has rebar going upwards, the rebar rods going up, the pillar going across the top has rebar rods going across the top, and what the contractors do is just chop the ends off and then plus over the top. But in an earthquake, what happens is you get lots of horizontal motion, and these just get pulled out like that. There's no strength in that corner. The corner's often the weakest part of that building. And the fix to this is really, really simple. All you do is bend the rods in, and that corner is now really strong. And again, no extra money, just a simple engineering tweak gives it the strong corner. And this is what happens when buildings aren't built properly. Some of you all remember this. There's a factory that collapsed in Bangladesh. And this didn't need an earthquake. These were just poorly built, misused, and badly designed factory that's just collapsed on its own because it didn't need an earthquake. And unfortunately, over 1,000 people died in this. And what worries me is that all of Bangladesh is like this. And Bangladesh hasn't had a big earthquake in a long time. And if all the buildings are this quality, what might happen in an earthquake? And that's really what worries me more about this situation. 1,000 people is an awful number of people, but it could be so much worse if there's an earthquake. So moving on slightly now to another element of my talk. I've talked about earthquakes a lot, but earthquakes aren't the only hazards we deal with in the world. And unfortunately, in the world there's many natural hazards. I was lucky enough to spend some time working in Istanbul. Istanbul is a city, this is the Black Sea in the north, this is the Marmara Sea, and that's the Bosphorus Straits there. Istanbul sort of straddles this strait. That strait marks, Europe and Asia. Asia's on the right here, on the left here. And there's a big tectonic fault that runs on right beneath it, the North Anatolian Fault. So, and this has generated really large earthquakes in the past. In fact, in 1509, it destroyed the city, and it was called the Lesser Judgment Day because it produced a tsunami, and all the churches and everything collapsed. So Istanbul has an earthquake problem. Istanbul also has a landslide problem, a flooding problem, subsidence problem, drought problem, hailstorm problem. In fact, it has almost every problem other than avalanche. And so it clearly, we can't just worry about one hazard. This is one location that has to worry about all the hazards. It's a hazardous place to be. What we wanted to do is figure out what is the relationship between one hazard triggering another hazard. So we know the simple examples of a storm might trigger landslides, but we want to know what are the full suite of connections that can happen between different hazards. And this is a list of hazards we created. There are 23 hazards, and from earthquakes to volcanic processes to hailstorms, snowstorms, and even meteorite impacts. What we did is sort of created this table to look at every possible way any one of these hazards could trigger another one. So the primary hazard, if to read this table, do need to remember the detail. The primary hazard here is on the left, and the secondary hazard is going across. So, for example, an example would be an earthquake here can trigger another earthquake, or an earthquake can trigger a tsunami. And you can go across and fill out this table and then figure out how one hazard triggers another. But how is this useful? This is useful now, so we can build this sort of hazard cascades that are realistic hazard cascades, or I call domino hazards. And I'm going to illustrate this with a simple example. So hopefully one that you will all know. So we know earthquakes can trigger tsunamis, and we've seen examples of that. Earthquakes can also trigger landslides. Landslides can block rivers, and they can make floods. So this is what I would call a simple multi-hazard cascade. And these are very common. This is an example of one from a few years ago in Japan. There's a big earthquake, a magnitude 9 earthquake in Japan, which triggered a tsunami. You will have seen videos of this. The earthquake also triggered a landslide. This is a landslide that blocked a reservoir and which caused a flood. The interesting thing in this earthquake was that it also had a very man-made impact. The tsunami destroyed the generators of the nuclear power plant that caused another man-made disaster. So this is a fascinating example of a natural hazard causing a man-made hazard disaster. And the problem now is trying to figure out what to do during this process. How do you keep people safe, given that it's not just an earthquake we need to worry about? We need to worry about the earthquake and the tsunami and the landslide and the floods. And this is an example of how the kind of things we need to think about. This is a little model example I've created of a town that's lives by the sea and there's by a river. And this is the ideal sort of city by the sea sort of scenario. So there's been an earthquake, right? And what do people do? They run outside after the earthquake, hopefully. And what should you do then is run uphill, right? Because what's coming? That tsunami is coming. So it's anything from 15 to 20 minutes later, that tsunami is coming. If the earthquake shaking lasts more than a minute, there's going to be a tsunami, more than likely. So we should run uphill. So this gentleman's done all the right things. But what about that person who cannot escape and get uphill fast enough? There was an earthquake in Turkey, Izmir, in the middle of the COVID pandemic, actually, or just after the COVID pandemic, which generated a small tsunami. And only 2 people died. Oh, I think only 1 person died, actually. And that 1 person survived the earthquake, and she was killed by the tsunami because she just couldn't get away quick enough. So her particular vulnerability is much different to the able-bodied person's vulnerability, given to the same hazard. What about those people? People with families, elderly, pregnant. And so each one of these categories of people, I should say, have very unique and specific vulnerabilities to any one of those hazards. And so that's the tsunami. But what about the landslide? So if people run up the hill, guess what happens after an earthquake? You get landslides. So how do we make sure that when you run uphill, you don't make yourself more exposed to the next hazard? And those landslides often block rivers, and these cities are located near rivers, and then it floods. And that might happen not instantly, but it may happen weeks later. And so, there's this whole sequence and cascades of things we need to worry about. So what I'm really getting at is that in reality, in the real world, it's not just the one hazard. One hazard triggers a change, what we call a change in exposure, and to the next hazard. And the next hazard, your vulnerabilities might be different to the next hazard because you may not have been worrying about landslides if you're in your apartment block in the city. But now that you're living in a tent on the hill slope, you should be worried about landslides because your vulnerabilities change to them. So what we say is that changing in vulnerability, exposure and vulnerability during a hazard scenario means your risk evolves over time too. This is what we call dynamic risk and dynamic exposure and dynamic vulnerability. And this is really the forefront of hazards research is how do we quantify all this? Because all we've got so far is drawing models like this with toy pictures. We haven't figured out how to put numbers to all this yet. And that's the real front of current research. So I've given a bit of a morbid view of hazards research, hazards at the moment. But what I really want to end on is that it's not all bad news, right? The world has actually getting much better at dealing with hazards, natural hazards and their impacts on humanity. So this is one of my favorite graphs, not because it shows deaths, but it shows the decrease in deaths from natural events, hazards. And in the early 1900s, over 500,000 people a year were dying due to some sort of natural hazard event. And now it's around 10,000 to 20,000, which is still a lot of people on average, but a lot less than 500,000. And this drop has happened principally in the sort of droughts and floods and categories. So these really big deaths in the 40s and 20s are from droughts, enormous droughts, and this big one in the 1930s in floods. And we're getting much better at managing fatalities from these two events now. Droughts being famine. When there are very few famines these days, even when there are drought conditions. Same with floods. Floods cause a lot of economic damage to the world now, but they tend to not kill as many people anymore, which is great. Here's another way of looking at this. Sorry, I thought that was a question to me. Again, the top figure is the ball. The size of the ball is the number of fatalities in all the hazards, disasters. And you can see the droughts here. There are loads of people dying in droughts in the early parts of the last century, and floods too. And these cycles have really dramatically dropped in size over the years. Two I want to draw your eye to is the earthquake. Earthquakes have been more or less random over time in terms of the way they impact people. And that's the real sort of call to not be complacent about earthquakes. We are getting better at dealing with other hazards. Earthquake is the one that tends to surprise us still to this day. And this is one that I worry about a lot. This is basically climate change, extreme temperature. Before, in the early 1900s, people didn't really care about extreme temperature impacting people's lives. But more and more these days, you're getting these heat waves that are causing a lot of fatalities in the world. You will remember the heat wave of last summer. I think that killed around 15 to 20,000 people in Europe. That one heat wave alone killed more deaths than the Nepal earthquake. So this is an increasingly worrying hazard, and it's only going to get worse. So we need to keep our eye on this, and we need to put measures in place to manage the hazard and risk from this, but it's not beyond our means. So to summarize, simply, earthquakes are caused by the release of strain energy on faults. Most deaths happen in the continental interiors in earthquakes between magnitude 7 and 8. And the vulnerabilities from exposure, the four horsemen, exposure, poverty, corruption, and ignorance, is what turns a natural hazard into a disaster. These four horsemen is what make disasters. If you want to really understand risk and mitigate their impacts, we shouldn't be siloed as physical scientists. We need to understand that the physical elements of an environment has to combined with the social environments in which people live. Otherwise, you're not really going to understand the impact of disasters or hazards on people. And we need to be aware that the world isn't so simple as one hazard. We live in complex, dynamic hazard situations, and so we need to understand the dynamic nature of multi-hazard risks if we really want to improve lives and save lives. I'll end there. Thank you very much. Hopefully, I have time for questions, but please tell me off if I've overrun or something.
Thank you very much, Iqbal, for this presentation. It's a good one to start the year, get us thinking about what we can do to improve other people's lives and our lives. It looks like the world in general needs to be re-educated when it comes to engineering for earthquakes, particularly in helping poor societies into making sure that people build better homes for themselves when they move from huts to permanent structures.
Mm-hmm.
Yeah. Do you have any questions for Iqbal? If you do, you can either unmute and ask, or you can put them in the chat.
While people are typing or are thinking, I just comment on that. So we know how to build the buildings withstand earthquakes, almost any size earthquakes for that matter. And engineers are amazing people. You give them a problem and they'll find a solution to it. The critical problem isn't the fact that we know how to build buildings to survive earthquakes, it's to build buildings cheaply that survived earthquakes. And particularly when we're talking about places like Afghanistan or Iran or Nepal, where you simply cannot afford the budget of a Japanese skyscraper, or who can build their buildings on springs and isolators and all that. So the critical problem is how do you build it in the way that uses local materials and minimal cost, and that's where we're struggling at the moment. We can make a house safe enough. And let us we can sort of accept a certain level of risk, and that becomes a very political problem. We do this in the UK, by the way. UK has this thing called the National Security Risk Register, and on it are all the risks that you and I face on a daily basis. Anything from a potential volcanic event in Iceland causing air traffic to drop, flood, pandemic, terrorism, anything that you could have any risk to, is on this graph. And all the government does is gives, I hate to say this, gives how much money is it worth saving lives for? Because no one has infinite amounts of money, and there's certain risk you're going to have to accept. And that number is a closely guarded political secret. So I would not want to be making that choice.
No, you wouldn't want to be making that decision. No, not at all. You mentioned something in yours, I think it was probably one of the last slides, about the rise in temperatures, just change in the climate change issue. In your research, or have you seen any changes that would affect earthquakes?
It's an interesting question, because if you'd asked me this about 5-6 years ago, I would say absolutely not. Earthquakes are random processes, more or less. But there are some tantalizing, interesting observations being released now by researchers. So not because of the temperature, but the temperature impact. So for example, sorry, that's my cat. If he interrupts you, I apologize. So there's a paper that was published in California, where the Central Valley of California, over the last several decades now, has been experienced very dramatic droughts. So the water level and water table in the ground has been reducing quite a bit. So that's actually a lot of material that's been disappearing from the ground. It's a weight that's disappearing. And it's in the scheme of earthquake tectonics, it's not a lot of weight, right?
Yeah.
But the idea is that it's the last straw that, I hate this expression, but it's the last straw that breaks the camel's back kind of idea.
Yeah.
The fault's just about to go, but this sudden drop in pressure, because all the water is disappearing, is enough to trigger the earthquake. So that's a really interesting result coming out. We know definitely that earthquakes in Iceland increased in the last 10,000 years because of the loss of the ice sheets. that weight disappeared,
The
and all
rebound
that
effect. Yeah.
and all that stress is now still redistributed in the crust, and that produces earthquakes. Same in Scandinavia, and that's arguably a climate consequence.
Okay, that's interesting. Don't see any questions on the chart. I think it must have been a very good presentation, Egbal.
But everyone's got it.
Yeah, everyone's got it. They have no questions.
or they say,
Yeah. Oh, we've got one. Andy says, is the UN aware of the impact of poor building practices in poorer countries? Is it doing anything about education?
Absolutely, the UN is definitely aware. In fact, some of them, they pay us to do this for them sometimes. No, they are aware, and there are some brilliant scientists in the UN working on this. The issue always is funding finances. And there are amazing examples where you can do this really well. So in Nepal, there's an organization called NSET, which started off as just one person with a good idea wanted to go and make people's lives better. And they did it so well that it's now part of a government ministry, where it started off as a charity. And what they did was just went out into the villages and trained people on how to build their homes for free.
Oh, that's good.
And it was quite simple. It was like a 3-week course. It wasn't even a long course. They said, this is how you mix cement, this is how you lay your bricks, this the corner, then the corners. Those simple engineering tricks I mentioned, it doesn't cost money. Just simple tricks and design features where the masons are going to build their homes by themselves anyway. So they might as well learn simple tricks to build it better. So these buildings aren't going to survive magnitude 8, 9 earthquakes, but they'll survive the ones that happen more often, 6s and high 6s.
Yeah.
And they also went through a program in the last few years, retrofitting schools in Kathmandu. And amazingly, in that earthquake in Nepal in 2015, none of the schools that they retrofitted collapsed. Of all the schools that collapsed, none of them were the ones, even though they were in the high shaking zone. And the retrofitting program was not expensive at all, by any measure of building a whole school. It was just they stuck rebar rods around it in a big grid, and that was it. And that was enough. So there are very simple tricks. So what we're trying to do is, UN is a very big sort of bureaucratic monster, and it often different parts of it do the same thing without realizing it's doing the same thing. So what you want to do is try and fund the most effective, cheap interventions rather than trying to do these big, enormous global catastrophe models that are useful for the insurance company, but less useful for the school who needs to protect its children.
Yeah, that's very interesting. The education part, that's quite interesting to know. Yeah, it's definitely worth going into these villages and poor countries and educating people.
It's also often it's about often enhancing their knowledge. They know what to do, right? They know how to build their homes with bamboo, and don't stop them. Don't get on with it. It's also just giving them that empowerment that just to know that what they're doing is doing that something in a good way, or in slightly little tweaks will make it even better. We never approach this problem as we know better than you.
No.
And that's almost often not the case.
There's a reason why the other structures were standing up in the first place.
Exactly. There's an interesting case here where you may have seen this amazing photo after the 2004 earthquake and tsunami of this one mosque in the middle of all this disaster. And one mosque stood, everything was destroyed. That itself is a fascinating example. In Istanbul, they're big, if you've been to Istanbul, these big mosques, they withstood all the earthquakes. Everything else collapsed. These big religious structures stayed. And one might think of that as a religious sign. Others might think actually people care about their religious buildings. So they spend more effort and money building them. And often they over-engineer it. They make the pillars bigger than they need to because it looks nice. But all that does is makes the building safe. And often actually it's safer to be in a religious structure than it is in your own home in some of these places, because people build them with care and over-engineer them. Yeah,
that's quite interesting. We've got another one from Mike. He says, what is the source of the data for the disaster time series graphic in your penultimate slide?
That's from, I think that's from the MDAT website. And that's the, let me get this right, the epidemiology of disaster. Oh gosh, sorry about yeah, I think it's a Belgian organization called Epidemiology of Disasters, something like that, MDAT, the database. But the particular graphic itself is from Our World in Data, which is an amazing website, which I wish you all visit. It's not just about earthquake and disasters, about everything, all the data in the world, about everything, really. And it's a cool, cool website, managed by a group in Oxford.
Do you mind putting that in the chat at some point so we take note?
Yeah, so the website I got that from is ourworldindata.org. A lot of my graphics are from there, actually. I love that website. And the database is the MDAT database for disasters. There we go.
All right. Thank you for that. We've got another one from Andy. He says maybe insurance companies should help to fund education programs.
That is true. And they do, actually, amazingly. I mean, we often sort of think of insurance companies as out there trying to take all your money, which to some extent they are. But there are many of them do actually do a lot of good stuff in terms of trying to help people. They do fund programs, but not enough. These are sort of corporate social responsibility initiatives, not hugely organized sort of focused programs. But insurance companies do fund research often on disaster management, disaster governance, disaster resilience. So they're not all bad. Most of them are, they're trying to actually help people. And insurance is an important thing. Insurance is a way to rebuild yourself afterwards. So I focus most of my research on building the resilience before the disaster, so that disaster doesn't happen.
Yeah.
The hazard doesn't cause a disaster. The insurance companies are there to lift you up after the hazard and disaster. So there's a space, and there's a really important space for them. But what we want to do is prevent the disaster. They're there to help you afterwards. So we need everyone on board here to do this, to work on this and that.
True. We've got one from Vicky, and she says, poor building construction is a clear problem. Are there similar problems for poor quality infrastructure, such as water supply, sewage, etc., and knock-on hazards after an earthquake?
Oh, absolutely. Absolutely. So actually, one of the main problems after the earthquake, tsunami in 2004 was water quality issues. And it's actually often the biggest killer sometimes. In Haiti, after the earthquake, killed a huge number of people, but it was the cholera afterwards that killed a lot more. And it wasn't, I mean, the earthquake itself killed way more people.
Yeah.
But the cholera killed a lot of people as well afterwards, because simply the health infrastructure, the water quality issues, just couldn't deal with it. So often one of the first bits of aid that gets flown in is water and medicine. Because you can't trust whether with your water supply. And so actually, pipes, water pipes, electricity grids, water, electricity pylons, all that stuff matter. After this hurricane in, I think, Puerto Rico a few years ago, one of the main things the British Army and the Navy did was to try and get the electricity coming on and go on as soon as possible.
Yeah, I can see how that would be.
These are primary, needs for people.
Yeah. Okay. Another one from Joshua. He says, is there a solution for multi-hazard events that you cannot engineer your way out of? For example, catastrophic glacial lake outbursts, floods following landslides. Is mentioned the Chamoli. Is that how? Yeah. Disaster in India, for example. Is the solution to persuade people to leave or build elsewhere, which is often problematic for a variety of social, political reasons, or are there other options?
No, this is a really important and interesting point, because you're right. Sometimes we just have to accept that risk, and governments have to, because people need to live somewhere. They need to live somewhere, and often they're at this high risk areas because that's the only place there is left to live. That's acceptable to them and their communities. And so this is a really deeply social issue about China has done this quite a lot. In the defense, I can't believe I'm defending the Chinese Communist Party, but in defense of the Communist Party, its intention is to protect people. So what it does is says, we're moving you all. And it just picks up villages and moves them away from where it thinks it's going to be a hazard, which in a sense is protecting them, but in a bad sense, it's completely ignoring all the social context. People are attuned to their landscapes, their homes, their environments, to their geographies. And if you ignore all that, then you're not really helping people. You're making their physical environment safer, but their social environment not as safe anymore. And both need to be done. So I'm with you there. It's a really difficult problem to work on, and we can mitigate some of the risk with engineering, by building the dams, this sort of or bypasses for gloughs and things. But you can't really stop it. And so, what is the acceptable level of risk here? And what can the communities do to mitigate their risk? So maybe they'll have to give up their farmland or whatever when the glough happens, but at least their lives will be saved. So what are the measures we can do to sort of lower that risk as much as possible, if we can't completely get rid of it? And that's where politicians and local authorities and people in communities, all these words that are non-physical science words, really become important.
Yeah. Same issue with building around volcanoes, isn't it? Or
Absolutely.
to big rivers, and people just build there because it's closer to I suppose good land that they can farm. So yeah, it's difficult moving people away from these situations.
Yeah. And this is why I'm a huge fan and supporter. All my students now get sent off to social science courses, because we cannot solve these problems with just mathematics and models, computer models. It's about talking to people, talking to governments, talking to public communities, engaging in conversations, doing all the dirty work of writing things on post-it notes and all that stuff. Mathematical models only take you so far. It's all about people at the end of the day.
Yeah, you have to understand why they're there.
Exactly. Yeah.
Yeah. We've got last one from Angela, and she said, was the research question you needed help with regard to assessing populations in multi-story buildings?
It's a bit of both. So one thing what we have done in the past, or do at the moment, is we make estimates. So we usually get the census data from most countries in the world, and make an estimate, say in one 500-meter box, there's 400 masonry buildings, 300 single-story buildings, 200 four-story buildings, etc. And what we do is try and divide up the population into those buildings, and that's the best we can do at the moment. Obviously, for some structures, we have much detailed information, but if you want to do a countrywide assessment, you can't go in every building and count every people. That's hard to do unless your local authority. So one thing we want to do is systematically make really good estimates of where people live, and yes, in multi-story buildings, and what floor people live in, and how many people are in each floor. But the problem is, it's not just that. It's about what time of day. In the daytime, a residential block has very different population size to nighttime. Yeah. And to time, to bank holidays, to weekends, to Wednesday versus Monday. So these are all complexities that come in now. And we just average everything at the moment because we can't deal with that complexity. We really need to. It doesn't matter if the earthquake is at midday versus 2 a.m.
No, it doesn't.
It's completely different. So anyone who knows clever ways of dealing with that, measuring it for one, will be happy to listen to you.
That's out there for anyone who's interested in doing some more research. Do contact Egbal. All right, I think we'll probably stop it here. But thank you very much, Egbal, for this presentation. It's been an eye-opener. It's very engaging. Thank you very much for that.
Thank you for having me. Thanks everyone for the great questions.
Yes, yeah. And also, we will be posting this on the YouTube channel once the Geological Society has gone through it for moderation purposes. So if anyone has missed it, if any of your colleagues have missed it and they wanted to watch it, do let them know it's on YouTube. And before we go, let me just share my screen. Next month, our talk will be a chartership event with Eleanor Williams, the new chartership officer. And this is a face-to-face meeting at the ACOM offices in Basingstoke. The Zoom details will be sent out as usual. Office, you can come into the offices from 6:30. There's parking as well. So do let us know in advance. We'll be sending this out. I think it's a joint meeting between the Thames Valley and the Solent group. So we're expecting a bit of a larger crowd, hopefully. So if you want to be a chartership officer, assessor, or you want to get chartered as a chartered geologist or chartered scientist, do come in and ask questions, because I know there are some changes that have been implemented since Eleanor's taking over as chartership officer. So we hope to see you in person on the 22nd of February. We will have some goodies as well to make sure that you're not starving after work. So thank you again and have a great evening.
Bye, everyone.
Bye. Bye, Iqbal. Thank you.